Hello, it's Mr. Claudia here, and today we're going to be looking at, we're going to continue learning the binomial distribution backstory. Last lesson we learned about combinations. Today we're going to continue and learn about Pascal's triangle. You've probably covered a little bit of Pascal's triangle for an ISU that you did or didn't do in grade 10 or 11. But because I know it was an ISU, you didn't really learn it, we're going to try going over a little more detail. So Pascal's triangle is this really neat mathematical array. It's this kind of beautiful math sequence. To build Pascal's triangle, we start with the number 1. And we always have 1 along the edges of the triangle. To find unknowns, so there's 1 and 1. So now for the row 2, to find the unknown values, I add the 2 numbers diagonally above it. So 1 plus 1 gives me 2. To find this value, 1 plus 2 gives me 3. To find this value here, 3 plus 3 gives me 6. And I can continue building this forever. Now there's just a few notes about how the Pascal's triangle work. The first thing is that we would call this row 0, element 0. This is row 1, element 0. This is element 1. So even though there are 2 elements here, we count from 0 to 1. This is kind of like programming. For those of you who do programming, you always start counting at 0. Similar with the rows, we're on the second row, but it's actually the row number 1. So row 0, 1, 2, 3, etc. Okay, the next thing we already talked about, the first value, so element 0, and the last value, or element n, are always 1, no matter which row you're in. So another point, we have row 4 then would have 5 values, 1, 2, 3, 4, 5. You always have 1 extra. Right? Row 0 has 1 element. Make sure you use this kind of designation, row and element, to refer to any value. So the first number would be the row, the second number would be the value. Row 3, element 2, 0, 1, 2. Now, can we use our knowledge of Pascal's triangle to build row number 5? Well, sure. Row number 4 had 5 values. Row number 6 has 6 values. So I'm going to draw the diagonal. This number and this number are always 1. To find the next element, 1 plus 5 gives me 4. 1 plus 4 gives me 5. 4 plus 6 gives me 10. 6 plus 10 and 5. And you can notice the symmetry here, right? There's a certain kind of balance to the Pascal's triangle. Mathematicians really like this. We call it Pascal's triangle because it was popularized by the French mathematician Blaise Pascal, but this is a good example of history not being remembered correctly, and Europeans kind of choosing to write math in a Eurocentric way. But this Pascal's triangle was discovered centuries and centuries earlier by other mathematicians, and it was first studied that we know of by the Persian astronomer Omar Khayyam. So, a little bit of TOK there. The math you know is only the math you've been told. Okay, what is the third element of the 6th row? So one way I could solve this is I could write out row 5 again, which is 1, 5, 10, 10, 5, 1. And then I could write out row 6, which would be 1, 6, 15, 20, 15, 6, 1. Again, there's that symmetry. So third element. So this would be the 0th element, the first, the second, the third. So it'd be 20. Now this would be hard. Imagine if I asked you to find the 80th row. You'd have to write out a lot of rows. But we actually observe that the elements of Pascal's triangle are actually combinations in the form row choose element. Wow, so it links back to our combinations lesson yesterday. If I want to know row 6, element 3, I go 6, choose 3. I type that into my calculator. 6, choose 3, and that gives me 20. This is very powerful because now I can find any one of Pascal's triangle number values by using combinations. So this is a neat math link. So we can do it ourselves. Second row, second element. Well, this would be choose 2. 2, choose 2. Oh, it's just 1. And that makes sense because the nth value is always 1. What about 4, choose 2? 4, choose 2. That's 6, which makes sense. The fourth row, second element is 6. Oh, and then here we go. 20th row, choose 5. This would take me forever to do, but fortunately I have my calculators. 20, choose 5. So it would be 15,504. That's a lot quicker than making Pascal's triangle. However, if you did want to write out Pascal's triangle, it wouldn't be so difficult. For example, for row 7, the first element would be 7, choose 0. Then we have 7, choose 1, 7, choose 2, 7, choose 3, 7, choose 4, 7, choose 8. Oh, 5. Jeez. 7, choose 6, 7, choose 7. And remember, how many, for row 7, there's 1, 2, 3, 4, 5, 6, 7, 8 elements because we start with 0. If I type this into my calculator, well, I'm just going to write them out, but 1, 7, 21, 35, 35, 21, 7, 1. And again, note that nice symmetry. So you can start to imagine Pascal's triangle not as a bunch of numbers, but as a bunch of combinations. Let's see if you can do that. Now, the question is, why are we learning Pascal's triangle? What's the point? There's a few different reasons. Now, the first is that mathematicians love it. It's a very beautiful sequence. It can be used to find a lot of things, like triangular numbers, pyramidal numbers, perfect squares, Fibonacci sequence, which a lot of you find interesting, can be linked back to this, and this kind of neat fractals image. It's called the Sierpinski triangle. It links back to Pascal's triangle. So there's a lot of connections to math, and so those are all things you could Google if you had some time. The other reason we like it is because we can use it to imagine and understand combinations. For example, if you want to build a hamburger, 7 condiments and groups of 2, you would use 7, choose 2. We already did this on the other side. 7, choose 2, it's 21. 21 different ways. You could have solved that using Pascal's triangle, so we like that linkage. But the number one reason we learn Pascal's triangle, and the reason it links to this course and what we're going to be doing, is binomial expansion. Now, those two words hopefully mean something to you, but if they don't, let's just review what binomial expansion is. Binomial, it's like a bicycle. It means you have 2 terms. And expansion means you're expanding these 2 terms when they've been squared or raised to a power. So a plus b to the power of 1, that's just a plus b. What about a plus b squared? Well, that would be a plus b times a plus b. Now you guys learned how to do this. We taught you how to FOIL. This is going to be a squared plus ab plus ab plus b squared. So that's a squared plus 2ab plus b squared. And okay, what if I had to do a plus b cubed? Well, this would be a plus b squared times a plus b. So it would be what I got from the last question, a squared plus 2ab plus b squared times a plus b. And you guys know this is a lot of work. Now I have to FOIL. So a squared, okay, so I'm going to get a cubed plus a squared b plus 2a squared b plus 2ab squared plus ab squared plus b cubed. If I simplify this a little bit, I get a cubed plus, okay, so there's 3 of these terms, a squared b, plus 3 of these terms, ab squared, plus b3. Can you imagine how much work this is? I mean, a plus b to the power 4, we just grown. I don't want to do it. I'll write it out for you. It's a to the power of 4, but I'm not going to show you the work. a3b plus 6a squared b squared plus 4ab cubed plus b to the power of 4. So Pascal's triangle helps us do this binomial expansion because look at these expanded values. Look at the coefficients. 1, 2, 1. 1, 3, 3, 1. 1, 4, 6, 4, 1. Look back at Pascal's triangle. 1, 2, 1. 1, 3, 3, 1. 1, 4, 6, 4, 1. They're the same values. So Pascal's triangle can actually be used to find the coefficients of a binomial expansion. And this is a huge thing for us. This is why we teach you this. They are from Pascal's triangle. Double exclamation mark. So this idea that I can figure out the expansion of any two terms using Pascal's triangle, this is called the binomial theorem. A plus b to the power of n, to the power of any value, is going to be, okay, well, actually we can kind of look and build this a little bit ourselves. So we see that the first term, so if I have a to the power of 1, or sorry, a plus b to the power of 1, so it's just a, here it's just a, here it's just a, here it's just a, but it's to the power of what I'm raising to. So I end up with n choose 0, a to the n, b to the 0, plus n choose 1, a to the n minus 1, b to the 1, plus n choose 2, a to the n minus 2, b to the 2, plus dot 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 dot, plus n choose n, a, o, b, n. Wow, it looks like hieroglyphics. But let's put this in a box. This is actually in your formula sheet. So it is something we should know, and it is not as intimidating as it looks. The other way I could write it is a plus b to the power of n is equal to the sum of r equals 0 to n choose r, a to the n minus r, b to the r. And that probably even looks worse. So I'll let you copy it down, or pause the video right now and copy it down. So let's look at how this works. If I want to expand a plus b to the power of n, well, my coefficients, here they are right here. I've already talked about them. They're just Pascal's triangle. So n choose 0, n choose 1, n choose 2, etc., 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 n choose n. So those are just the numbers. 1, 4, 6, 4, 1. Next we have the a's. Now look what happens to the a's. We start with a to the power of whatever I'm raising it to. So a to the power of n. Then I go down, and I go down, I continue to go down until I get no a's. And look, you can see that here. A to the 4, a to the 3, a to the 2, a to the 1, no a's. And the b's do the opposite. I start with no b's, and I go b to the power of 1, b to the power of 2, b to the power of etc., all the way up to b to whatever I was raising. And again, you have no b's, b1, b2, b3, b4. So you get the a's going down, the b's going up, and you get the constants from the Pascal's triangle, or from combinations. The compact way of writing this is a sum. So sum, remember the sigma means add up all of these different terms. There's how I calculate the coefficient. There's how I calculate the a power and the b power. And r is is my element number going up from 0 to whatever n is. So from say 0 to 4. Okay, so now I can use binomial theorem to expand any power. So for example, I have a plus 5. Actually, make sure you write over to the side here so you have enough space. A plus 5 to the power, a plus b to the power of 5. Okay, well, let's do the coefficients. So it's going to be 5, choose 0. And then I have a to the power of 5. Oh yeah, my a start out at the top, and my b starts out at 0. Okay, then my next term is 5, choose 1. It's the next entry into the Pascal's triangle. My a's gone down by 1, my b's gone up by 1. Okay, 5, choose 2. Now my a is at 3, b is at 2. Plus 5, choose 3. A is now at 2, b is at 3. Okay, plus 5, choose 4, a1, b4, and then we have 5, choose 5, a0, b5. And you can simplify this a little bit. I mean, 5 choose 0 is always going to be 1. You can remember the side values of my Pascal's triangle, always 1. You can type this in your calculator. Similarly, 5 choose 5 is always 1. A to the power of 0 is 1, and b to the power of 0 is 1. So my final answer is going to be a to the power of 5 plus 5. This 5 choose 1 is just 5, a4b. 5 choose 2, look at my Pascal's triangle, type it in, that's 10, so that's 10, a3, b2. 5 choose 3 is 5, that's that's 10 again, sorry, I didn't write that down right. A squared b cubed plus 5 a b4 plus b5. So there we go. We're able to do some pretty amazing things using Pascal's triangle. Now, and this is setting us up for tomorrow's lesson, you can have slightly more complicated binomial expansions. I mean, this is still a binomial expansion. It's a first term, a second term, raised to the power of something. But the x's aren't going to line up perfectly. It doesn't have a very neat a and b. It has a lot more going on. But we can still use the equation to help us do this expansion. So give yourself lots of space here. Let's go through this systematically. So first we have 4 choose 0. That's my first term, right? 4 choose 0. Then, well, let's just, before we do this, this is a, this is b. So for all of these questions, I have that all of these expansions of terms, a is equal to x, b is equal to negative 2 over x, and n is equal to 4. So we have 4 choose 0. Then I need the a, so that's x, to the power of 4. And I need the b, negative 2 over x to the power of 0. Okay, second term, 4 choose 1. I have x, but this time to the power of 3. b is negative 2 over x. This time it's to the power of 1. We're going to continue. 4 choose 2. X to the power of 2. Then my b value is negative 2 over x, but this time to the power of 2. Because remember, the b values are going from 0, 1, 2, and they're going up. And the x values, the a values, are going down to 4, 3, 2. 4 choose 3. X to the power of 1. Negative 2 over x to the power of 3. And finally, 4 choose 4, x to the power of 0, negative 2 over x to the power of 4. Now, we're done using binomial expansion. I just have to clean things up. Well, remember, this is 0, or this is 1, and this is 1. Similarly, this is 1, and this is 1. So those ones are easy. I end up with x to the power of 4. 4 choose 1 is just 4. I end up with x cubed. Now negative 2 over x, well that's just negative 2 over x, like that. Then I end up with 6 x squared. Okay, negative 2 over x squared is going to be 4 over x squared. And then my next term is 4x. This time I have negative 2 cubed, so that would be negative 8 over x cubed. And then finally we get 1 times 1. This is going to be, oops, you can't see, negative 2 over x to the power of 4 is going to be 16 over x squared. Okay, and now we're almost there. Just have to do some algebra and clean this up. This is going to cancel with this and leave me with 2 x's. This is going to cancel with this. This is going to cancel with this and leave me 2 x's. So I end up with x to the power of 4 minus 8x squared plus 6 times 4 is 24 minus 32 over x squared plus 16 over x to the power 4. So you can see this has that nice kind of symmetry. It's very orderly. You can see this one doesn't, but there are some patterns here. The first term, the x's, because you have an x in the denominator, that's canceling out some x's. But your result is still a pattern. X to the power 4, x to the power of 2, x to the power of 0, x to the power of negative 2, x to the power of negative 4. And you can see the negative in this original expansion term creates a negative, it's alternating signs, so a negative, positive, negative, positive. So there's still patterns here, but it's a lot harder to predict this pattern. That's why we have to be very methodical when we use Pascal binomial expansion for this sort of question. Your homework for this section is in the another section or another chapter, the sequence and series chapter, page 187, number 1 to 8. And I'm going to say that you're going to need to use your GDC or just your calculator, right? I showed you how to do this on a regular calculator. Good luck with that, and until next time.